So one example is one main challenge is the unavailability of stable, inexpensive, and highly efficient semiconductor materials. And if we are looking at the Z scheme or two photoelectrode based photoelectrochemical water splitting reactor, then we need to have the two materials which have band edge positions compatible to each other. So at the moment, the combination of two materials, one can act as a photoanode for oxygen evolution and one can act as a photocathode for hydrogen evolution has been not discovered or optimized yet. The third problem is the improper interfacial charge transfer dynamics. So the charge carrier are once the charges are produced at the surface of material, the separation of the charges and moving those charges to the respective oxygen evolution and hydrogen evolution sites is a bit slow, which cause lower efficiency. So what we are looking at is a cheap, abundant, and non-toxic material, stable in aqueous environment, low cost fabrication, and their band gap should be between 1.8 to 2.1 electron volt. Band edge position should be above and below the redox level of water, which is 0 to 1.2. So most of the known materials like titanium dioxide, zinc dioxide, tungsten, which are very stable, iron oxide, and easily abundant and low cost. However, their band, either they have the large band gap, so they cannot absorb the visible light of the solar spectrum, or their conduction band edge position is below the reduction reaction of water where hydrogen evolution takes place. And while the materials such as cadmium sulfide, cadmium selenide, gallium phosphide, and many other materials who has in the right band edge positions, but most of them are not stable under the redox conditions of water. So they immediately convert into oxides, and once they convert into oxides, so their band gap and band edge positions changes, and they no longer are suitable for the water splitting. So in my research group, so we are looking at the discovery of the stable materials. So first of all, we used soft chemistry or green synthesis for the fabrication of a photoelectrode directly, and that can be through the single molecule precursor or using a range of low temperature deposition techniques. As in this case, the cheapest substrate is the fluorine doped tin oxide coated glass substrate. So which maximum temperature we can go is around 600 to 650. So all these materials need to be fabricated below that temperature. The next area which we are looking at to discover is the metal ferrites. So metal ferrites are a new class of materials which has both N-type, which can act as oxygen evolution materials, and P-types, which can act as hydrogen evolution materials, as well as due to the AbO3 or Ab2O4 formula. So these materials are much easier to dope, change their electronic properties or band gap and band edge position. So our current focus is discovering the metal ferrites as suitable materials for photoelectrochemical water splitting. Improving the light harvesting efficiency of these materials, either controlling their nano architecture and nanostructure, or using other techniques like doping and surface treatment. Kinetics and mechanism of water splitting. So we also investigate how the water splitting reactions takes place onto the surface of these semiconductor materials using a range of spectroscopic techniques. And also looking on to a single particle Z scheme water splitting. So where the one particle can do both the reactions, as we have seen in Professor Dominic's talk, that the main material can be loaded with the co-catalyst to make it suitable for direct water splitting. So the research expertise, so mainly we are looking onto the computational approach combined with the range of experimental fabrication techniques to make these materials, and then we use these materials in the range of applications. However, the one of the focus is solar fuel, where we make these photocatalytic materials and then use for hydrogen evolution. The other area where we are looking as onto the electrocatalyst, as we know that from the renewable energy technologies now in many countries we can generate excess of electricity, and the storage of electricity and transportation of electricity is a very big challenge. So the other option is that using the electrocatalyst we can convert that electricity into hydrogen by splitting water, and then use that hydrogen as a transport and storable fuel. So because the topic is onto the hydrogen, so I will keep focus my talk onto hydrogen. And then the fabrication and characterization methodology. So we use state-of-the-art techniques to make these materials. As I said that yeah, we are making these materials onto FTO, which is a tin oxide coated glass substrates, and the temperature range need to be maximum to 650 below the softening temperature of glass. So for that one, we use the spray pyrolysis and chemical vapor deposition techniques. In the beginning, to discover the materials, we make large number of small samples and then anneal them on different temperatures, and then using the electrochemical and photoelectrochemical techniques, we immediately characterize those ones, the materials which are photoactive under these conditions. Then we tune them for their to analyze for the band gap and band edge positions, and then use those ones for photoelectrochemical water splitting. While the materials which does not have a suitable band gap, they can be used for environmental applications, and the materials which are electrocapacitive under electrochemical conditions, we can try to use those ones in electrochemical energy storage, or use them for the electrocatalyst in water splitting. And the more detail of the technologies which we use is aerosol assisted chemical vapor deposition, atmospheric pressure chemical vapor deposition, and then aerosol assisted vapor transport deposition, spray pyrolysis, and physical vapor deposition. So these are some of the techniques which we use for the fabrication of materials in our laboratory. So next is some selected examples on the design or discovery of the suitable materials for photoelectrochemical water splitting. So we use both computational simulation or DFT study, as well as experimental fabrication and evolution of the properties of selected materials. So one of the thing, as the tantalum oxynitride and tantalum nitride is one of the well are the potential materials which can be used for water splitting, and they have a right band gap and band edge positions, as we have seen from Professor Domino's work, that they have done a lot substantial work onto optimization of these tantalum nitride and tantalum oxynitride materials. So using the computational study, we have found that the tantalum oxynitride, if it is deposited in 010 orientation, and if it is deposited in 001 orientation, So the phase which has 001 orientation has the band gap of 2.11 and its formation energy is 2.01, while the phase with the 010 is oxygen terminated and has a band gap of 3.01, where the formation of energy of 0.00. So when we are doing these reactions inside the water, so it is very important that the surface termination play a key role in the reaction kinetics as well as the rate of reactions. So if the material is terminated by oxygen, so it will be partially negative at the surface, and when it is partially negative at the surface, it will attract more hydrogen ions, H ions or protons in the electrolyte or in water, and will proceed hydrogen evolution reaction more efficiently compared to if the material is terminated by the other metal ions or surfaces. So similarly, when we are looked onto the DFT study, and we found that the band gap is also dependent onto the phase. And if we have a 001 or 001 oriented phase, so the band gap is 2.11, which has the ability to absorb more solar spectrum compared to the phase which has 010, where the band gap changes to 3.01, so which will absorb a slightly less portion of the visible spectrum. Another example is the bismuth vanadate. So bismuth vanadate is also one of the well-studied material in photoelectrochemical water splitting, and again, bismuth vanadate can be in different phases, and then we have discovered this material and looked onto the interaction of water onto the surface of bismuth vanadate in the pristine phase, as well as creating some defects using the selenium dioxide onto the surface of this material. And as a result, we have found that the bismuth vanadate in 001 phase is much stable and has a right band gap and band edge positions for the photoelectrochemical water splitting. And then the surface defects can be created using the selenium doping into the pristine bismuth vanadate to improve its efficiency. So the next example is selenium bismuth vanadate heterostructure. So instead of doping the selenium into the bismuth vanadate, and our theoretical studies shows that if we have a layered structure, then the band gap will be more incompatible with each other to compensate the charge generation. So the bismuth selenium will absorb light and generate electron and holes. The selenium has a higher conduction band edge, so has the potential to generate hydrogen and carry on the redox reaction, whereas the bismuth vanadate has a lower conduction band, so its power to carry on the reduction reaction is lower, so it can be used as an oxygen evolving materials, and then the charge generated by the bismuth vanadate will compensate the holes onto the selenium. So in this way, the reaction will proceed with much more efficiency. So using these computational simulations, then we have made these materials practically, as well as also looked onto the different options that if we have the selenium is deposited onto the substrate first, and then bismuth vanadate onto top of that one, or we have the bismuth vanadate deposited onto the substrate and selenium on top of those ones, or we have the co-deposition of both instead of having the layers. So finally, our electrochemical studies and photocurrent study shows that if we have the selenium deposited onto the substrate and then bismuth vanadate on top of that one in layered form, has much higher efficiency and produced much more photocurrent compared to the other combinations, and which directly align to our computational study. And then using the more Schottky plot, we have calculated the band edge and band edge positions and band gap positions, and finally concluded that the layered structure of selenium and bismuth vanadate is a right combination for direct water splitting using the sunlight. Similarly, we also looked onto the heterostructures of tungsten trioxide with gallium nitride, as well as using the gold as surface plasmonic resonance to increase the light absorption efficiency of the heterostructure. And the theoretical studies prove that the gold nanoparticles are able to generate surface plasmonic resonance and help to absorb more sunlight onto the main material, whereas the band edge positions of tungsten trioxide and gallium and gamma carbon nitride are aligned with each other for the direct water splitting. And the TEM images shows that the material has been formed in the form of heterostructure, where we can say that the main material is gamma carbon nitrides, and the tungsten trioxide is embedded into it, and the gold nanoparticles are present onto the surface of the heterostructure. And then using the range of spectroscopic techniques, we have found out there the absorption range and absorption edge to calculate the band edge positions and band gap positions. So the material has been used for the dye degradation as well as for the hydrogen evolution reactions. And we also have tested the stability of the materials after recycling, and in 4 continuous cycles, we can say that the material has are able to produce hydrogen in small quantity, as well as recycling and reusability indicate that the material is stable and can be used for a range of reactions, as well as we also looked onto the different combinations of these materials to see that if the material has a better efficiency by using the UV visible light, and it indicates that compared to the visible solar spectrum with the UV visible, it produced much more hydrogen compared to the normal UV light, which is due to the plasmonic resonance as well as the effect of the UV onto the material. And then simple oxide. So we also looked onto the iron oxide. So iron oxide is another well-known material. And we looked onto the effect of orientation onto the photocatalytic performance. So iron oxide can be deposited in the form of 104 oriented films or 110 oriented films. So when the iron oxide is deposited in the 104 oriented orientation, so it is oxygen terminated crystal structure, while when the iron oxide is in 110 orientation, so it is iron terminated crystal. So when it is oxygen terminated, so it has a partial negative charge onto the surface, while when it is iron terminated, so it has a partial positive charge. So as the iron oxide has a lower conduction band than the redox reaction of water, so iron oxide can be used as a photoanode or for oxygen evolution reaction in water. So when it is oxygen evolution reaction, so it has to interact with the OH ions in the electrolyte or in water. And for the OH ion interaction, it is preferred that the iron should have a partial positive charge, or it should have been terminated by 110 orientation. So using our fabrication technologies, so by changing the fabrication parameters, we have made the iron oxide from 104 oriented film to 110 oriented film, and then using the photoelectrochemical performance studies, we found that the iron oxide, which is 110 oriented, has much higher photocurrent and performance compared to the iron oxide, which is 104 oriented film. Similarly, using the impedance measurements, we calculate the flat band potential, and with respect to the pH. So the data shows that the films which are 104 oriented, they does not follow the Nernst equation, where the flat band potential should move 59 millivolts per pH. However, the films which are 110 oriented, they follow the trend more regularly, and prove that the 110 oriented iron oxide has much better performance and efficiency. And then using the range of spectroscopic techniques, which include intensity modulation, photocurrent spectroscopy, potential modulated absorption spectroscopy, light modulated absorption spectroscopy, and transient photospectroscopy. So we have developed a mechanism of oxygen evolution on alpha hematite as a photoanode. So our studies shows that first the iron 3 with one hole, or by losing one electron, goes into iron 4. And in the second step, iron 4 takes another hole and goes into iron 5. And then the iron 5 will react with the OH ions to generate to regenerate the iron 3 and oxygen from water. So this is the scheme 1, and at the same time another scheme where the iron 4 directly react with the OH ions plus hole, and then regenerate the iron 3 and oxygen. So both schemes compete with each other, and as a result, so the analysis shows that we need to have some way the storing of the holes onto the surface of alpha hematite is necessary, and that is one of the barrier why the performance of these materials is very low, because storing of these holes as the water splitting is a 4 electron process. So storing these 3 or 4 holes is very difficult, and that brings the recombination element into the reactions. As a result, the most of the electron generated once the holes are stored onto the surface recombine with the existing hole instead of moving to the cathode or to the counter electrode to generate hydrogen. So for that reason, some of these materials required external bias, so we can pull out the generated electrons so that they can transport to the counter electrode for hydrogen generation. So, and as in the beginning I said that currently we are exploring metal ferrites as a potential materials because of their ability to act as P-type materials or photocathode, as well as N-type materials to act as a photoanode in photoelectrochemical water splitting reaction. So one of the example is zinc ferrite. So we have made the zinc ferrite using a simple single molecular precursor and aerosol assisted chemical vapor deposition. From the SCM, we can say that a well-oriented highly nanostructured film has been produced onto the FTO substrate, and then The photoelectrochemical study shows that the material is photoactive as well as has the ability to act as a photoanode in the photoelectrochemical water splitting reactor. The Morse-Schottky plot proves that the material has a conduction band of 0.2, which is not suitable for the hydrogen evolution, but can be used as an oxygen evolution reaction. And then the IPC indicate that the efficiency of a photon to electron conversion efficiency is around 13%. And then we looked on to another copper ferrite as a photocathode for the photoelectrochemical water splitting, and you can see that the film deposited by aerosol-assisted chemical vapor deposition has a well-oriented nanostructure, and particles are grown directly from the substrate to the top, which provide enough space for the electrolyte to penetrate in and take the electrons to generate hydrogen from these materials. Whereas the XRD shows that a single phase material has been deposited using the simple chemical vapor deposition technique. The photoelectrochemical studies prove that the material is photoactive as well as act as a photocathode and is a P-type material and has produced about 1.2 milliamps of photocurrent at 0.3 versus reversible hydrogen electrodes. And the stability shows that the material is stable for a longer period of time, as well as the photoelectrochemical conversion efficiency shows that the material has an efficiency of around 13%. And then we looked on to another group of ferrites, which has the formula of AbO3, and these materials are more perovskite structure and has ability to accept more dopants and easily surface tunable. So the material is deposited using a spray pyrolysis technique, and SCM shows that the film is porous with well-connected zigzag structure with each other. XRD prove that the material is a single phase with cubic or perovskite structure, while the optical study shows that the material has a band gap of 2.4 electron volt. The photoelectrochemical studies prove that the material is a photoanode and is P-type and act as a photocathode while producing substantial amount of photocurrent under the visible light or solar simulator. The stability study shows that the material is stable. We have tested this one for up to 33 days. However, for the data and due to the chopping reason, the data is shown for only 20 hours, and the material has been chopped continuously to evaluate the effect of any charge accumulation onto the surface. The IPC shows that the overall efficiency is low compared to the other materials. However, the film is semi-transparent and can be used in tandem cell assembly where it can absorb a part of the solar spectrum, while the rest of the light can be absorbed by the second material in a tandem assembly to generate hydrogen and oxygen simultaneously. And then we have improved the efficiency of lanthanum ferrite using the nickel and the silver as plasmonic nanoparticles onto the surface. And it proves that both the silver and the nickel has improved the efficiency more than twice than the simple lanthanum iron oxide. Similarly, by using these nanoparticles, the stability of the material has not affected. So it means that after the plasmonic nanoparticles, the material has the same stability as it has before. And then we have used this material as in a simple photoelectrochemical reactor. And the material has shown excellent performance while it can produce the hydrogen by its own without the use of any photoanode. And then we have measured the hydrogen evolution with time, and it indicates that the performance is steady and the material can produce hydrogen without the use of a photoanode. While as on to the other hand, by using the nanoparticles, the performance of hydrogen evolution has been increased to a substantial range. At the same time, we are now discovering the combining this photocathode material with another ferrite-based photoanode material in a parallel assembly where one can generate hydrogen and other can generate oxygen. However, these experiments are in progress. So next, I would like to highlight some of the work which we are looking at onto the electrocatalyst material for water splitting. So in electrocatalyst, as I said, that now the renewable energy technologies are able to generate surplus electricity, and that surplus electricity can also be converted into into the hydrogen, and then hydrogen can be stored and transported. For that one, we are looking onto the development of oxygen evolution electrocatalyst. We are looking at hydrogen evolution electrocatalyst, as well as looking onto the design and reactor scale up. And our work is more focused onto the alkaline membrane compared to the existing proton membranes, because the alkaline membrane has much lower over potential and will use much lower electricity compared to the existing proton based membranes. So in this direction, our work is more focused on to the doping of the catalyst to lower the over potential, which will ultimately improve the efficiency of those materials, exposing the sites and the binding energy calculation, so activity and stability of these materials. So we are looking at how active and stable these materials are. Activation barrier and reaction network. So in this case, for the electrocatalyst, it's very important that the electrocatalyst should be selective and it should not react with any impurity or any other dissolved gases into the water. So the selectivity is one of the key parameters. Hydrogen bonding for water electrolysis activity. The more the hydrogen bonding, that will be the activity. And also looking onto the CO2 bonding, which cause the poisoning to the system or reduce the activity of the material. So we are looking onto the material which has a low CO2 bonding energy. So some of the selected examples of hydrogen evolution reaction and oxygen evolution reaction. So first is iron oxide encapsulated within the graphitic carbon nanotubes for efficient hydrogen evolution catalyst. So first we modeled these ones using the computational DFT study, and found that if we embedded iron oxide inside the graphitic nanotubes, how the band structure will be, and what will be the effect of this one onto the surface, as well as the onto the electron density difference. So which indicate that materials has very good overlap with each other, and they can be used as a combined material for an efficient electrocatalyst. Then the XPS studies, then we made these materials, and XPS study shows that yes, the material is in a heterostructure, and TEM proves that the iron oxide is embedded inside the graphitic carbon nanotubes. Then the electrochemical studies shows that the material has much lower over potential and has the capacity to act as electrocatalyst in for hydrogen evolution in electrocatalytic reaction. And the continuous cyclic study shows that the material remains stable at different scan rates, as well as using the different number of cycles. And then finally, we looked onto the efficiency of this material inside the reactor, and it shows that the material is stable and has the ability to produce hydrogen from water and in catalytic reaction. So the next is the nickel iron cobalt ternary oxyhydrate for efficient and stable ORE electrocatalyst. So in this case, again, first the material which is nickel iron cobalt oxyhydride is suitable to act as an oxygen evolution catalyst. But however, which percentage and composition will be more suitable and effective? So first, we theoretically modeled different phases as well as combination of these materials, like only nickel oxyhydrate, which is one of the materials which can act as an oxygen evolution catalyst, and look down to its affinity with the water or effect of water onto the surface. Then we put 15% iron into the main nickel oxide oxyhydrate, and then look down to the effect of water onto the surface. Then we add instead of iron, add 15% of cobalt, and look onto the theoretical studies. And then finally, we combine both 15% iron and 15% cobalt into nickel oxyhydride. And then found that this is the material which has the best electrocatalytic activities, as well as its surface energy is much higher, so it can be used as a best electrocatalyst. And then we have developed this material. We deposited this material using electrodeposition technique onto the nickel mesh, and then use this material for the electrochemical studies. And electrochemical studies shows that the current density of this material is on much lower potential compared to the existing materials. Material has a much higher stability, and it can be used in at different temperatures as well as at different experimental conditions. And finally, we found that if we have the nickel, iron, and cobalt in 70, 15, and 15 composition, so its oxygen evolution potential is 556 millivolts, and over potential is 256 millivolts, which is much lower compared to most of the single metal oxide or double metal oxide hydrides used as an electrocatalyst for oxygen evolution reaction in alkaline membrane. And lastly, I would just share some of the SEM images of different materials which we have tried and tested for photoelectrochemical oxygen evolution, and either due to their lower performance or stability. So these materials are not selected as a potential materials for oxygen for water splitting using sunlight. And I would like to acknowledge the researchers who has contributed to the work shown onto my slides, which includes my PhD and postdocs, as well as some visiting researchers, funding agencies, which include UK as well as the British Council and European Union to execute this work, and other collaborators who one way or the other has contributed to this work. Thank you very much for listening, and any question?
Thank you, Dr. Asif. So the participants, if you have a question, you can type in the chat meanwhile. And Doctor, there is a question from my side. You discussed about nickel, iron, cobalt catalyst for oxygen evolution reactions.
Yes.
I am very new to this area, so it's maybe very basic question. Is there any sequence that we have to deposit or introduce the metals? For example, you did nickel over iron and then cobalt. Is the sequence can be reversed, and what could be the?
No, in this case it is not a sequence. It's basically it's a composite material where we have figured out the composition of these materials into that one. So it's in other words, because the composition is above the doping limit. So if it is below 5%, then we can say that this is iron and cobalt doped nickel oxyhydrate. But because the composition which we found out theoretically as well as experimentally is well above the doping limit, so we will call it as a composite material.
Okay, thank you. And Doctor, there is some question. What is the maximum rate of the hydrogen production is reported in your studies?
So in our studies, we take it either to the Faraday efficiency or into the hydrogen quantity. So the material like lanthanum iron oxide, which I have shown, has a 30% Faraday efficiency. And if we are looking onto the hydrogen, at the moment, the amount of hydrogen is in micromoles, not in millimoles, as Professor Domino has shown on the powder based. However, if this technique is successful, then it will have a much lower cost compared to the other reactors where the separation cost will be a separate issue. And in this case, we will have a direct separation because both oxygen and hydrogen will evolve at two different ends.
There was one more question I'm trying to. Oh, okay. There is a question from Ahmed Taleb. He wants to know, can you please elaborate on the effects of band gap of this semiconductor metal oxide on water splitting? Because this is a critical point for catalyst design, and we need to understand the fundamental aspects.
Yes. So the band gap, so there is, whether the band gap, it's not only the band gap. So there are three things we need to consider. First is the band gap. So band gap means that if we have the band gap between 1.8 to 2.1 means that we will be able to harvest most of the solar spectrum. And which means that we can harvest not only the solar spectrum, it's more to the visible light. And that's not the only criteria. And then it comes to the like, for example, if we are looking onto I'm sure you are able to see my slides yet, yeah?
Yes, can you little zoom it is better.
So then we have if we have the band gap, for example, we have the band gap for iron oxide is 2.1 and the zinc ferrite is 1.9. Now they have the ability to absorb most of the solar spectrum, so they will be a brick red in color or close to that one. So their band edge position will be around 600 nanometer in that range. However, the next comes the band edge positions. So after the band gap, we have the band edge positions. So where the valence band and conduction band lies. So if the band edge positions are not right, for example, in both cases, we can see that the conduction band is much lower than the zero on NHE, which is the reduction potential for water or hydrogen evolution potential. So if this conduction band is lower than that, which means that the material will not be able to drive the hydrogen evolution reaction, it can still be able to drive the oxygen evolution reaction. And that also makes it another parameter. So we need to find the material which in both cases, so if we are looking onto the example of say cadmium sulfide or cadmium selenide, so the both has the band gap in within the range, and their conduction band edge positions are right to drive these reactions. And then it comes to the stability issue. If you are choosing two materials, so next is that instead of having a single material, why not we can take the two materials. If we are taking the two materials, then we need to find out a best way So something like that, we have to find out where the valence and conduction band of the one material and where is the valence and conduction band of the second material and how the electron transport will take place. If the gaps between these, the valence band of the one material and conduction band of the second material is too high, so the electron will not transport from the one material to the other depending upon which material is you are taking as an hydrogen evolution material or photocathode, and which material you are taking as a photoanode or oxygen evolution material. So in this case, what is important is that the electrons generated by the oxygen evolution material should be able to move or to the transport to the valence band of the hydrogen evolution material, so they can compensate the charge generated onto the photocathode. So these are the three fundamental things which we need, and then it comes to the charge transport properties, how quickly or easily the charge will be transported.
Excellent, excellent explanation, Doctor. Doctor, because we are running out of the time, and once again, I would like to thank you on behalf of all the participants and Chemical Engineering Department and KFUPM for your time, especially early in the morning, and sharing with your valuable research with us. Hope we will be in touch for the future invitation and hopefully in physical. So in that case, we will provide you the breakfast and a lot of coffee. Don't worry. So thank you. Thank you very much, Dr. Asif.